Welcome in, guys. Let's go ahead and get started. Right at the sort of beginning of the session today, I want to announce that I'm going to be doing some tutoring. If you have any questions on any concepts or anything, you can come by, and I will be in McLean 167. That's the room right over here. Tomorrow, Thursday morning, and Monday, later in the evening. So, give you a variety of times to choose from. You can write this down. Also, I got an email from a chemistry student who is also offering tutoring, free tutoring in the science building. So you can come take a look at this. They are doing Friday, 1 to 3:30. So that's also an option. You can come down after the, I can't get it to show up here at the moment. I'll put it up at the end of class. They're doing like a Zoom thing, and you could also go in person. This is all for the exam that's going to be next Thursday, so a week from today. Let's see. I'm thinking, I'm having a lot of questions about it, and I'm gauging how fast I'm going. I think on Tuesday, I'll do a bit of review of the previous, chapters we've been doing. So I'll do about, half of the class will be dedicated to looking at some stuff we've already done. All right. Also, I think today is going to be fairly short. I keep things fairly slower pace since we're getting ready for that exam. All right. Again, we have tutoring tomorrow, 10 a.m. to 12 p.m. So that's noon. And then Monday, 4:30 to 6:30. I will just be sitting in a room alone, waiting for you guys to come in and ask questions. All right, let's sort of recap. Yeah.
So exams on all the topics that we did so far?
On all of the stuff we've done so far, so I'm going to say, like assignment 1 to 6. So that's, we've done like vectors and motion and forces, all the way up till, I'm going to say, momentum. So none of this rotation stuff will be on this exam. That doesn't mean you put off this stuff too long, because it's going to be on another exam in the future.
When's the exam again?
Next Thursday. So a week from today. Yeah.
So is there still homework due next Thursday?
Yes. I'm going to make it sort of a relaxing weekend after that, since we are having an exam. I'll let you know on the day. All right? So, and if you have more questions on, exam stuff, material, all that, I'm going to be going over it on Tuesday. Probably a, good sort of review, recap. All right. So let's sort of recap what we've learned already with rotation. So we have objects that may move in other ways. Things may spin or spin around one another thing. Things that rotate will always have an axis of rotation. That's sort of this line that cuts through anything that spins. All right, what else did we learn about rotation? Well, we learned that when we, break away all of the, new changes, I'm using new symbols, all of this new terminology. What we learned is that it's exactly the same as just motion for a linear object. So instead of something being displaced and it being called delta x, now it's called an angular displacement, and it's called this angular displacement. So What kind of angle is this thing sweeping through? We've also learned that there is an equivalence to velocity. Instead of just velocity, we have angular velocity. That's this Greek letter omega. This is a lowercase omega. You see it typed out. It looks a little fancier than that even. This is how fast the thing is rotating. And that's purely just how much of the angle does it sweep over a certain amount of time. So that's just simply that over that. Right? Same exact thing as in a linear case. Finally, we also saw there is acceleration. Instead of linear acceleration that we had just a regular a, we now have angular acceleration. That is this alpha. Right here. You can probably guess what this equals. This is just the change of your angular velocity. Change of angular velocity in however much time you're doing or measuring for. All right, so, yeah.
Does the W stand for work?
No, that's a no, omega. It's not actually a W. It looks kind of like, if you see it typed, it looks like, or so it's a lowercase omega, Greek letter, and it's just for angular velocity. Let's get rid of that. Okay. So, since we have all of these things that match up just about 1-to-1 with things that were linear, things, I was just rolling things across the table, or I was, throwing things, something that's moving in a line, something that is on an air track, just moving in a line. Since they're almost directly, equal, we also saw that there was kinematic equations for things that rotate. So there are rotational kinematic equations. And let's go ahead and refresh ourselves what those look like. We're going to do that on the next slide. Okay, so these are exactly the same format, just with the new terminology. So I always kind of start out with this first one. There is no particular order to any of these, but we have angular velocity, all right, so that looks familiar. It's just using different symbols. Then we have that second one. Plus 1/2 alpha t squared. And I'm just going to write 3 down. These are 3 of the more important ones. We have the last. Plus 2 alpha delta B. Theta, sorry. So, if you memorized those ones before, these are a breeze. You're going to only use these though, remember, can only use these if there is a constant angular acceleration. Let me fix that. I'll say use for there. Constant angular acceleration. And that also, applies to if the angular acceleration is 0. That's just a constant value of 0. That's why we were able to use these on, those previous chapters. All right. So now that we're sort of caught up, we can look at some new things with rotation. We have, let's go like that. All right. So let's say I have a ball on a string like this. And which way to go? I start to spin it around and around. Right? Yeah. Not hit you guys in the front. Okay. Now, let's say I cut the string somewhere. And let's cut the string right where the picture describes it. So that's going to be near the bottom, right? So it's sort of a thing moving in a circle, and I cut the string that's holding it to my hand. Where's the ball going to go? Right? Let me draw the string, and I'll draw the string, and now I've cut it. Is the ball going to go that way? Or is it going to go that way? That way? So A, B, or C? What do you guys think? B. So it's going to follow the path that it was originally going, right? And right when it's no longer tethered to my hand, it is going to go in a straight line. So, right, B is the correct answer. So let me get rid of that one. Okay, same thing, spinning around and around, except now this time it's at the top somewhere. Sort of at the top, near the edge, kind of off center. And right when it's up here, I cut the line. What's going to happen? Where is it going to go? And let's consider that, I know if I cut it at a certain place, it's going to go and it's going to arc somewhere. Let's consider that this is like no gravity, nothing's affecting it, just where's the immediate direction it's going to point to, right? So, right at this moment, it's going to go kind of like that, right? I can make that better. Like that. I have another one. I don't even have to do the spinning the ball around. Where is it going to go? It's going to go straight down. This is the moment right after I cut the string. It's going to go straight downward. So this line that I'm drawing, this arrow that I'm drawing, that is going to be called the tangential velocity. So at this moment, it has angular velocity, but as soon as I let it go or cut the string or whatever, it disconnects itself, it's going to go in a straight line and have a linear path. So this is tangential velocity, and it continuously sweeps around the circle wherever it is. It's always moving. So if you cut it at any moment, it's going to go in that direction, whichever direction it is pointing. Right? Okay. Now, this thing is moving at a certain speed. The tangential velocity is a certain speed, right? Now, if I have it, the string is that long, it only has a radius, the circle I'm forming only has a radius of this. Whereas if I do the full thing, and I sweep the same amount of angle, you see this outer tennis ball on the edge, it's going to be covering a lot more distance in the same amount of time. And so, see, it's moving very quickly compared to the tangential velocity if I let it go at that moment. So that's a very rough version of what's happening. The size of the arrow is how fast it would be moving tangentially. This is a good thing to know. So I just started talking about things that rotate. Earlier we were talking about things that move in a line, and this is kind of showing how they're related. Things actually just want to move in a line all the time. That is, if you remember, that was Newton's first law. So let's put it right here. So Newton's first law, that was the law of inertia, right? It said things at rest tend to stay at rest, things at motion tend to stay in motion. Things at rest tend to stay at rest. And then the other line of this was things in motion, things tend to stay in motion. But I mentioned something when I talked about this, when we covered this. Things in motion tend to stay in linear motion. Or I could say straight line motion. And that wasn't a problem for us when we were going over that stuff earlier, because everything was moving in a line. Or maybe it was an arc, but it was still linear motion. This is something that's, it's being forced to do the same path over and over again. And now you can see, when I have this tennis ball, and I start to spin it, it doesn't like spinning. It doesn't like rotating like this. It wants to move in a straight line. So whenever I give it the chance to do it at once, it leaves. It goes into a straight line path. The earliest it can. Okay? So we can find these tangential components, how to convert from angular into straight line motion. All right, this is basically the conversion of the two. We can find the tangential velocity and tangential acceleration. And when I say the word tangential, that's just the same v velocity we've been using the whole semester so far. So I'm going to say v equals the radius of whatever sort of arc this thing's moving around times its angular velocity. And similarly, for tangential acceleration, we have just the regular acceleration, regular a we've been using so far, is equal to what kind of what kind of radius is this thing sweeping? What kind of a distance from the pivot point or axis of rotation? If it has a larger radius, it will have a larger tangential velocity. And what else do I have on this? I think a couple more things. All right, yeah, we'll do an example. So say we have a CD with the radius of 5 centimeters, 0.05 meters. It's initially at rest, and we sort of put in a CD player and start it up, and we begin to rotate it. It begins to rotate with a constant angular acceleration of 40 radians per second squared for an amount of time of 0.35 seconds. All right, what angle does the disk rotate through during this time? So that's sort of a confusing, trying to figure out what it's asking. What it's asking is, what is the angular displacement? That's what it's asking for. Next one is asking, what is the tangential velocity of the CD at this time? All right, so let's go ahead and find this angular displacement. How much does the CD spin? That's what the first question is asking. All right, so we know radius is this. We know angular acceleration. We know for how long. Okay. We also know one more thing. Question starts out by saying it's initially at rest. So its initial velocity or initial angular velocity is 0. Because it says right up here, initially at rest. And that's helpful. All right. So we have those written out. Yeah.
Is that radians per second or meters?
You got me. I was trying to trick you guys. Radians per second. Fast? Yes, we're good. All right. So we can look back at the, kinematic equations for, rotating objects. I've learned I don't want to fill up my space on the slides too early, so I'm going to write them over here on the board. And we have T, we have this one, and we have this one. Okay. So those are the equations I gave earlier. Right? Okay. Those are the rotational kinematic equations. Now, which one looks like it might help? The second one. Okay. We use the second one to find. It's pretty much already laid out. We don't have to rearrange it at all. Displacement right here. Acceleration time. What was initial rotational velocity? 0. So that will go away. And we're left with everything else that we know. Okay, so that will go to 0. All right, 40 radians per second squared. And 0.35 seconds squared. Okay, after we do all of that, we will get 2.45 radians. Awesome. So that's how much the CD spins, we're just tracking how many angles it sweeps through. All right. Next up was the tangential velocity of a CD at that moment, or at that time. So let's do tangential velocity. We learned earlier it is V equals R times rotational velocity. Do we have rotational velocity? We don't have it at that moment yet, right? We can find it. So how can we find rotational velocity, this omega right here? We use that first one, right? Okay. So let's do that. And we know that initially it starts at 0. Radians per second squared. And only 5 seconds have passed. All right, and we get 14 radians per second. And so, say we didn't see this equation, or we kind of lost a bit. A way I always, have a secret, shortcut, instead of doing this equation all the time, is just remember what acceleration means. So in this term, I'll do it. Angular acceleration is the change in angular velocity over the change in time, right? And so that's final minus initial, and final minus initial. You can do this for the linear acceleration as well. The same, like this. So I think I just put this up here earlier. Just like that. Yeah.
I think I did that one, but I got 7 instead of 14.
7 instead of 14.
Because I just did 2.45
Oh.
radians.
Oh, right. I'm not even done with the problem yet. Hold on. That's right. Right. So this is the angular velocity right here. That's angular velocity. That goes right here. I'm not done yet. I do this all the time. Okay. 14 times the radius of the CD. So we need to find the tangential velocity. I'll put it over here. Equals 0, 0.5. And that equals 0.7 meters per second. There we go. That is the tangential velocity. What I circled earlier was the angular velocity, the omega right there. All right, if I make mistakes like that, just tell me. All right. So that's sort of a typical rotation problem. It's very much, the same as what we've been doing so far. Just things moving, and it changed a little bit somehow, and figure out this new term. How much did it, turn? How much is it, accelerating? Things like that. So nothing too frightening. All right. So let's say we have a ball or a mass somewhere, and it's moving with a constant velocity. Let's say it's moving, for this thing, let's say it's moving this way. Let's see. How did I do this? Let's say it's moving down. That's the velocity. And I give this thing a push, or I give this some sort of acceleration to the right. So these are tangential. This is just, V and A. So I'm changing its acceleration horizontally, and I'm sort of making it speed up and go that way. But it has some constant velocity down that way. Which way is it going to go? So remember, acceleration is just like a speeding up or a slowing down. So it's speeding up as it's moving. It's sort of, going that way. It's sort of doing this. Right? And now let's do something down here. It's moving with the same velocity. Say it's going that way. But now I sort of push it another way. I have an acceleration that is pushing it this way. It's the same thing. It's the same sort of principles. I'm just looking at things left to right, up, down. It's moving up a little bit, but now it has to accelerate that way. So it's going to kind of turn again. Right? It's the same thing as that first picture. So let me make this like red. So it's going to accelerate and turn. It's going to be a turning sort of thing. If I do something up here, same process. There's a velocity, and I give it some acceleration that way. I just have this thing that's turning all the time. This is basically what's happening for something like this ball. It is trying to move in a straight line, but it is constantly feeling this acceleration that is turning it in different directions all the time. It's pointing that way at one moment, and then when it's down here, it's pointing that way. This is exactly what's happening with something that is moving in a circular motion. There's always this acceleration. It's changing its direction. At that moment, it's pushing it that way. It's down here, it's pushing it that way to make it turn. So we get something that is now moving in a circle. All right. This acceleration that it's feeling as it's being forced to turn all of the time, that is called centripetal acceleration. So I could put that right here. It's constantly making this thing turn. That's what I can label centripetal acceleration as. It's this acceleration that forces it to just keep turning and turning and turning in a circle. Imagine the x, y axis. This thing is constantly pushing it in a different direction as it starts to spin. That's sort of represented by this big orange arrow right here. And the green arrow right there, that's the direction that the ball wants to go in. That's the tangential velocity. So that is called centripetal acceleration. And it only does that. Remember, things are only ever changing their state currently, this mass on the table, will only ever move or change how it is if I force it. So for this acceleration, this thing spinning in a circle, something has to be forcing this to spin or forcing this to keep turning. That force that is making this acceleration is called centripetal force, or it's often just called centripetal force. And in the case of me doing this sort of your very simple ball on a string demo, the thing that is making the centripetal force is the tension in the string. It's always pointing towards the center. So the ball is always being forced to turn. It's always being forced to accelerate in a different direction that it doesn't want to go in. So centripetal force will continuously push an object towards the center of the rotation, whatever type of rotation it's doing. And so you can call centripetal force, you could call it a, let me put underneath it, you could call it a center seeking force. All right. Now, say we get to a point where we need to know how much this thing is being forced to turn. We need to know that centripetal acceleration. It's not tangential, because tangential is I put it up here. So a tangential acceleration is sort of along the path of the circle. So that is some sort of acceleration is going that way. That's tangential. If an acceleration is pointing inwards towards the center of rotation, that is this centripetal acceleration. Centripetal. Maybe we need to know that value. Maybe we need to know how much is it trying to turn? How much is it being forced to turn in this circle? That will determine whether this is a very lazy sort of spinning thing, or if this is like going around very quickly. How quick is it being forced to change its direction? So we may need C. So centripetal, you can just say A, C. So we can say that, and these are all terms that are linear, right? So we have just regular velocity and the radius of whatever is turning. I say also. Let's say we want to know based off of rotational velocity, rotational acceleration, things like that. Well, it's easy just to transfer over. Over r, and that will just equal r omega squared. So pretty much, like one of these r's cancels out. All right. Okay. So we have these things that always want to move in straight lines, but if it moves in a circle, it's being sort of forced to move in that circle, right? Bring that thing back up. We still have it. Yes, things always want to move in a straight line. And it's not until something pulls it inward that it will you'll begin to turn. Now, I'm going to explain this demo a bit more detail next time. I want to leave you guys with this and then one more sort of thing. So we have ball on a string, sure. You can see my hands holding it, but it's hard to interpret what's going on, because you don't know how much force my hand is applying and all this other stuff. So let's go like this. I'm going to hang a mass. This is 500 grams. And see, it weighs much more than the ball. Right? Okay? And this mass is applying a force downward, the force of gravity. It's the weight of this thing, right? Pulling down, it's tension in the string. Tension in the string. And what if I start to rotate this ball up here at the top? So if I don't go fast enough, it comes back to this sort of point right here. But if I rotate it faster and faster, the green arrow is going to get bigger. That means that the sort of orange arrow has to pull harder to turn it. So what we're going to get, something like this. Look at the mass down here. I can make it go up. This is related to the radius of whatever I'm spinning. It's moving much faster up there. If I slow down, so we have this tension, it's pulling it inward, and it's related to this changing acceleration, this changing force. It's always trying to force it to the middle. But the ball always wants to move in a straight line. I'm going to cover that a bit more later with an example. Last thing I want to show you guys for today is this thing right here. So I have a little tray, and I'm going to hold this cup right here on the top. Right? And sort of is able to stand on its own. We already know kind of the forces that are at play here. There's gravity, tensions upward, but it's sitting on this, so that's actually normal force with this surface. So the normal force from this plank is pointing up. what if I start to spin this thing? Well, what's going to happen if I put water in it? I put water in it. And I start to maybe jostle a little bit or rotate it. So I've only spilled this a little bit when I was practicing. So, say we have this thing, I can start to swing it back and forth, and there's tension, and the water in the cup wants to move in a straight line, but the tension in the rope is going to change its direction. That's why it's not sort of falling over right now. So what would happen if I applied a lot of force to get this thing to spin in a circle? So is the water going to fall out? Hopefully not. Right, so let's try it. I'm going to go over here. You guys are in this splash zone. Okay. If it doesn't work, I'm going to try it again until it works. Okay. So ready? And here we. Okay. Okay. So we have this centripetal force always forcing this thing to the middle. Do one more. Okay. Even with that. We have all right. So I'm going to start out next week with like finishing this chapter. Then we'll move on to the next chapter, and then we'll do a little review. That's Tuesday. If you guys have any questions or anything like that, you come to the tutoring tomorrow. There's also separate tutoring from this person. I'll see you guys next week.